In the last lecture, we were looking at a cylindrical coordinate system as an example of a curvilinear coordinate system, and we had derived balance equations for the cylindrical coordinate system by doing a balance over a cylindrical differential volume. Okay. This is used to analyze problems where one of the boundary surfaces is a cylindrical surface, and therefore, it is convenient to select one of the coordinates such that the boundary surface is a surface of constant coordinate. That coordinate is the radial coordinate, distance from the axis. So, you have one coordinate that is distance from the axis, a second coordinate that is distance along the axis, and the third is the angle around the axis, which we had referred to as phi earlier. And we had done a balance equation for a differential volume bounded by two cylindrical surfaces of constant coordinate, okay, at located at the inner surface located at the distance r, and the outer surface located at the distance r plus delta r. Okay, so, two surfaces, one is at the location r, the other is at the location r plus delta r. Okay. And two surfaces perpendicular to the axis at x and x plus delta x, two surfaces perpendicular to the r direction at r and r plus delta r. And we were considering unidirectional transport where variation is only in the radial direction. Okay. And the equations that we had derived were generally of the form, okay, partial of the field variable, okay, phi by partial t is equal to 1 by r d by dr of r times the diffusion coefficient times partial phi field variable by partial r. Sorry, let me just write this in terms of the flux first, times the generalized flux in the r direction plus s, okay, where the generalized flux could be the mass flux, the heat flux qr, the mass flux jr, or the momentum, the stress, the negative of the stress. Okay, so, I should have a negative sign here. Or the negative of the stress tau xr if the momentum is along the axial direction. The constitutive relation was jr is equal to minus d times partial phi field variable by partial r. Okay. Substitute that into the equation, the constitutive relation. Minus d is either the mass diffusion coefficient or the thermal diffusion coefficient, negative of the momentum diffusion coefficient, because there is no negative sign in Newton's law for viscosity. Okay. And when you express it finally in substitute this into the differential equation, you will get partial phi fv by partial t is equal to plus s, okay. And if the diffusivity is a constant, you will get plus s. Okay, so, these are the balance equations where phi is concentration for mass transport, temperature for heat transport, and Vx, the velocity in the x direction for momentum transport along the x direction. I had told you that for velocity in the phi direction around the axis. Okay. So, if you have two concentric cylinders which are rotating, for example, okay, with an inner velocity omega I and an outer velocity omega O, okay, there will be some velocity profile between the inner and the outer cylinders. Okay. In this case, the velocity is along the phi direction around the axis. Okay. The non-zero component of the velocity is v phi along the phi direction along the circles, okay, perpendicular to the axis and perpendicular to the radial direction. V phi is the polar velocity that varies with r, okay, and the equation for V phi is different. Plus F phi. Okay, I should put a rho here as well. Okay. Or in terms of the kinematic viscosity, partial V phi by partial T is equal to kinematic viscosity into d by dr of plus F phi by rho. Okay. And the expression for the stress is also different. Tau phi r is equal to mu okay, so those are the expressions. Okay. So only the polar velocity conservation equations and the stress are different. The other three have the same forms. Okay. So now let us consider steady solutions. No source or sink. Steady solutions and no source or sink. Okay. So the equation becomes, okay, 0 is equal to 1 by r d by dr of r alpha partial t by partial r. Okay. And if there is constant diffusivity as well, I get 0 is just equal to 1 by r d by dr of r. Okay, so that is the equation for steady solution with no sources or sinks. Okay. So let us consider a case where we have two cylinders, an annular region between two cylinders. Inner radius is Ri, outer radius is Ro. Okay. Inner temperature is Ti and outer temperature is To. Okay. And we would like to find out what is the temperature variation in between. Okay. If you recall, steady transport, no sources or sinks, constant diffusivity, Cartesian coordinate system, it was a linear function of z. Okay. The temperature field was a linear function of z. The flux was a constant. Okay. In this case, that is not true. Okay. So let us solve this problem. What we can do is substitute r star scale temperatures r by Ri, okay, and T star is equal to T minus Ti by difference between outer and inner temperature. Okay. I am just scaling the variables to express in terms of scaled coordinates. Okay. So at the inner cylinder, okay, r is equal to Ri, which means that r star is equal to 1. Okay. T is equal to Ti implies that T star is equal to 0. Okay. That is the condition on the inner cylinder. Okay. Outer, r is equal to Ro, which implies that r star is equal to T is equal to To, implies that T star equals 1. Okay. So those are the boundary conditions. Note that it is a second order differential equation, therefore, you can have two boundary conditions. Okay. And I can scale the equation, define R is equal to R I times R star, okay. And you can easily verify that the equation that you will get in the end, okay, 1 by R d by dr of R partial t by partial R is equal to 0 will transform to 1 by R star. And you can solve this. Okay. So, d by dr is equal to 0. Okay. Integrate once more, r star partial t by partial r is equal to a constant, okay, or partial t by partial r is equal to a by r. Okay. And therefore, t is equal to a ln of r plus b. Okay, t is equal to a ln of r, the natural logarithm of r plus b. Okay. Apply the boundary conditions. Okay. The first boundary condition is that at r star is equal to 1, t star is equal to 0. Okay. At r star is equal to 1, log, natural log is equal to 0, okay, which implies that, okay, b is equal to 0. Okay. And then at r star is equal to r o divided by r I, t star is equal to 1. Okay. T star is equal to 1 at r star is equal to r o by r I, and what that implies is that a is equal to 1 over ln of r o by r I. Okay. Therefore, the solution for the temperature field is T star, okay, so T star is equal to ln of r star by ln of r o by r I. Okay. This satisfies all the boundary conditions. When r star is 1, t star is 0. When r star is log of r o by r I, t star is equal to 1. Okay. So, this is the boundary, this is the solution for the conduction between two concentric cylinders. Okay. Now, QR, the heat flux, is equal to K partial T by partial R. Okay. Express this in terms of scaled variables, okay, minus K into TO minus TI, okay, divided by RI into, okay, partial of, okay, partial T star by partial R star. And what is partial T by partial R? Okay. Okay. So, this partial T by partial R is equal to the natural logarithm of R, the derivative of that, okay, is equal to QR is equal, sorry, the derivative of t with respect to r star is 1 over r star log of r o by r I. So, this is equal to minus k into T o minus T I by r I into 1 over r star ln of r o by r I. Note that R star is R divided by Ri. Okay. So, this just becomes equal to minus k into To minus Ti by ln of Ro by Ri, sorry, R into that, okay, because this combination R star times Ri is just equal to the unscaled radius R. Okay. That is the heat flux. Heat flux is not a constant, it goes as 1 over R. Okay. The total heat transfer rate, okay, the total heat transfer rate QR is equal to 2 pi R L into QR, okay, where L is the length, okay, along the axis. Okay. Okay, at any distance r from the axis, the cylindrical surface area is 2 pi r into L. Okay, the cylindrical surface area is 2 pi r into L. Okay. So, therefore, this is equal to 2 pi r L into q r, okay, is equal to minus 2 pi k T naught minus T I 2 pi k L. So, this heat flux is independent of R. Okay. You can see that there is no dependence on the distance from the axis in this heat transfer rate. The heat flux does depend inversely upon R. Okay. So, I told you that for a steady heat conduction, the heat transfer rate over any cylindrical surface has to be the same, because what comes in has to go out. The heat flux does not have to be the same, because the heat flux is the ratio of the heat transfer rate and the surface area. In a curvilinear coordinate system, the surface area changes as the radius changes, and therefore, the heat flux goes as 1 over the surface area or 1 over r, and if you multiply that by the surface area, which is 2 pi r L, the heat transfer rate is independent of position. Okay. So, this of course is different from what we had earlier. Okay. If you recall, what we had earlier for a Cartesian coordinate system was that q in the z direction is equal to minus k a, okay, delta, that is T difference in temperature by delta z. Okay. And if I try to express this same expression for the heat transfer rate in a cylindrical coordinate system, the equivalent would be minus k a into T naught minus T I by R naught minus R I, the thickness. Okay. Now, this if I just simplistically wrote this as QR, this is what I would get. Okay. Okay. On the other hand, the expression that I am actually getting is this one. Okay. So, this expression is obviously not correct unless this area is redefined in some way. Okay. That area, okay, it's called the logarithmic mean area. Okay. So, I get this logarithmic mean area by equating these two and selecting what should be the value of A in such a way that I get the correct heat transfer rate. Okay. So, if I equate these two, I will get minus k a L into T naught minus T I, okay, by R naught minus R I is equal to minus 2 pi k L into T naught minus T I by ln of R naught by R I. Okay. This expression basically defines what is A L. Okay. This expression defines what is A L. If I were to try to write an expression exactly the same as what I had for a Cartesian coordinate system. Okay. And this A L would be equal to 2 pi L into R naught minus R I by the logarithm of R naught by R I. Okay, which I can write as 2 pi L into R L, where this logarithmic mean radius is okay. So, if I substitute this in the expression, then I will be able to get the correct value of the heat flux. Okay. So, either you can use the exact expression that we have derived here. Okay, this is an exact expression that I have derived here, or if you want to use the expression that was already derived for a Cartesian coordinate system, okay, I have to define the area in here, okay, in such a way that I get this expression. Okay. Area cannot be the surface area. Surface area is changing as R changes. So, you do not have a unique surface area. In a Cartesian coordinate system, the surface area at any value of z was exactly the same. They were plane surfaces. Cylindrical coordinate system, it is not the same. Okay. If you want to use an equivalent area, then it has to be defined in this way. So, this is the solution for the temperature field and the flux. Okay. The temperature field T star is equal to log of R star by log of R O by R I. Okay. Alternatively, in unscaled variables, T minus T I by T O minus T I is equal to ln of R by R I by ln of R O by R I. Yeah. That is in unscaled variables. This is the solution in a cylindrical coordinate system. The heat flux QR is equal to minus K into TO minus TI by R ln of R O by R I. Okay. And the heat transfer rate is equal to 2 pi R L Q R. The heat transfer rate is independent of radius, the flux is not independent of radius. Okay. So, this was for a single pipe. Okay. What about if you have a composite? Okay. So, let us consider this case. So, this is R I. I will call this as R F in between the two, and this is R O. Okay. And let us say the inner surface is at temperature T I, the outer temperature is at T O. Okay. How do we calculate the temperature variation, the flux and the heat transfer rate? Okay. So, if the intermediate temperature is T F say, okay, if the intermediate temperature is Tf. Okay. Then we know that the radial flux, okay, so you have two slabs here, okay. One is this one, okay. The other is this outer one. Okay. Okay. You have two slabs here. Okay. For each slab we can determine the heat transfer rate as a function of the temperature difference. Okay. So, for the inner, Qr is equal to minus 2 pi k L. L is the length perpendicular to the plane in this case along the axis. Okay. Okay. Is equal to into Tf minus Ti by log Rf by Ri. Okay. And similarly, you can do the same for the outer. Okay. Qr is equal to minus 2 pi k L into To minus Tf by log Ro by Rf. Invert these two expressions. Tf minus Ti is equal to Qr log of Rf by Ri, okay, by it's a negative sign here, okay, 2 pi Kl. I should use a different conductivity here. The inner has conductivity Ki and the outer has conductivity Ko. Okay. So, then inner one has conductivity Ki, two different materials. Okay. So, the conductivities will in general be different. Okay. Ko is the outer conductivity and the inner one has conductivity Ki. Okay. Okay. And To minus Tf is equal to minus Qr log of Ro by Rf, okay, divided by 2 pi Ko L. Okay. Add these two and you will get Tf minus Ti is equal to minus Qr, okay, into log of Rf by Ri by 2 pi Kil plus log of Ro by Rf by 2 pi K outer into L. Okay. Recall when we did a Cartesian coordinate system, we had done the same thing for a composite slab. In that case, the difference in temperature was Ka into the heat transfer rate was Ka into delta T by H, where H was the thickness. In this case, the heat transfer rate is given by this. Okay. So, in that case, we had identified the heat transfer rate with the current and the temperature difference with the voltage, in which case this factor here was the resistance. Okay. These factors here were the resistance. Okay. In this case, we can also consider these as the resistances. Okay. So, this is the resistance for the outer, this for the inner, okay, and for the outer. Okay. So, I defined the resistance as equal to log of Ro by Ri by 2 pi K L. Okay. This is the heat transfer resistance. Note that when we did for heat transfer in a Cartesian coordinate system, this was R is equal to H by K A, okay, and A was equal to the area perpendicular to the Z coordinate. Okay. In this case, the resistance should be considered as log of Ro by Ri by 2 pi K L, where L is the distance perpendicular. Okay. Then if we have two slabs, okay, the total heat transfer resistance, okay, R is equal to Ro plus Ri, that is the resistance due to the inner slab plus the inner tube plus the resistance due to the outer tube. Okay. I have used calligraphic letters to distinguish this from the radius, which is capital R. Okay. So, this is the resistance, and each resistance, okay, is equal to log of the ratio of the radii divided by 2 pi k into L, okay, where k is the thermal conductivity. Okay. So, the same formulation that we had used for a series of slabs in the previous Cartesian coordinate system, where the resistance in that case was equal to h by Ka. Okay. That can also be used in order to, in the cylindrical coordinate system, except that the resistance has to be redefined. It is log of the ratio of the radii divided by 2 pi k into the distance perpendicular. Okay. You can verify easily that both have the same dimension. Okay. So, therefore, the total resistance, okay, so this should be T0 minus Ti, okay, which is equal to minus Qr into Ro plus Ri. Okay. In this series configuration, where the difference in temperature or the voltage difference is different, whereas the current or the heat transfer rate is the same, the resistance due to multiple slabs is the sum of the resistances of each of those. Okay. And this heat transfer resistance is log of the ratio of the radii divided by 2 pi k L. Okay. So, this is in the series configuration. Okay. If you recall, when we did heat transfer for slabs, we also had a parallel configuration where the temperature difference was the same, but the fluxes were different. Okay. That in this case would correspond to a configuration something like this, where I have different resistance materials in different segments of this annulus. Okay. So, I have one material here, another material here, and so on. Okay. In that case, you would have 1 over R is equal to 1 over R1 plus. Okay. So, that would be the parallel configuration. So, that analogy between series and parallel configurations, which we had earlier for heat conduction in flat slabs in a Cartesian coordinate systems, carries through to steady conduction in cylindrical annulus, provided this resistance is defined differently in this case. Okay. Provided this resistance is defined in this manner in this case, differently in this case. So, next class we will take a look at some examples of heat conduction in cylindrical coordinate systems, and we will solve some problems before we go to a spherical coordinate system after that. I will continue this in the next lecture. I will see you then.